Okay. So, what did we do was the following. Last time, we came to this part where we had a degeneration, a good degeneration, fraction of x5 into a normal crossing singular threefold. I call them y1 and y2 over some s. This s was a K3 surface. This y1 was the Quintic inside P4, and this y2 was some blow up along some complete intersection curve in P3. We had something like that. And then we used the degeneration formula to basically say that, so we were looking at the degeneration of the moduli space of H stable sheaves on x1. So these were sheaves on x1 with a given first Chern character, some Chern character vector, which was Chern character 0, H, some first class, and some n. And we said that this moduli space degenerates into two moduli spaces of sheaves on this side and on that side, and they meet along the K3 surface in the middle. And then, okay, so we have these things, and then we define this open loci inside of each moduli space, which was the capturing those sheaves whose support meets transversely the K3 surface in the middle. And we realized that those loci are open, and we need to compactify. And we saw, okay, so there is some mechanism, let's assume, that compactifies that, and those are the bubbling phenomena. So we have moduli space of H1 stable sheaves on Y1 with respect to S, with some choice of Chern character 1, and then we have the moduli space of H2 stable sheaves on Y2 relative to S with some Chern character 2. And both of these guys, these are compactifications of these moduli spaces. So interior points of these moduli spaces is the same as the interior point of just the moduli space of sheaves on Y1 or Y2 with the Chern character 1. The boundary points are exactly given by sheaves who satisfy the normality condition. So there was this normality condition, which was saying that if I take my sheaf in here, Tor over O of yi, 1 of our sheaf fi, with respect to this O of s, needs to vanish. And this normality condition was an open thing, and we needed to compactify based on that. If you did that, then the sheaves inside here and the sheaves inside here satisfy the property that their support meets transversely the K3 fiber in the middle. And so you have restriction maps by tensoring with the structural sheaf on the surface. You have these restriction maps, and then in the middle you will get the moduli space of some HS stable sheaves on this surface S with some Chern character S. And HS was isomorphic to either of HI's restricted to S. It was the hyperplane section on the surface. And Chern S was the Chern character of the restriction of FI's on the surface S. So we had this thing, and so we also discussed that this X5, because of being a Calabi-Yau, has virtual dimension 0, because of their seriality. This thing, well, it's a Fano threefold in P4, and you can calculate the virtual dimension from the following formula. And each one of these things, the virtual dimension is given by trace-free, counting the dimension of trace-free extensions between Fi, and so that's just 1 minus Euler characteristic, and the virtual dimension here is equal to 3. And the virtual dimension here is also equal to 3. And this one is nothing but the Mukhai's moduli space of sheaves which are supported on curves, and this was the smooth, and it was dimension 6. So I was asked a question like, why do we know, what is the evidence that the virtual class remains the same? I mean, the dimension, for example, remains the same, the virtual dimension. So the 0, It becomes 0 again. 3 plus 3 minus 6 is 0. And then we have this divisorial support map. So if you want it, you can call it divisor of the support of the f. F restricted to s. So support of f on s could be many things, but we are looking at the divisor of that. And why are we doing that? I mean, so because otherwise then we don't know how to deal with this, right? I mean, we could have a rank 2 sheaves on a curve or rank 1 sheaves on double curve, and then this map will be ill-defined. But we would like to send them to the divisor thing. So O of 2s, and O of 2 times a curve, and O plus O on a curve, I want them to be the same thing. And so, anyways, so this thing sends us to the linear system of hyperplane sections. If you like, you can call them hyperplane sections of this H of S, which are the curves of genus 3. And this is isomorphic to P3. So we have covered all of this. And since this is P3, its dimension is 3, so, and this is also, well, first of all, Mukai showed that this thing is a holomorphic symplectic manifold. So this thing is a holomorphic symplectic 6 complex dimensional manifold. And it comes with a holomorphic symplectic 2 form, which vanishes along the fibers. So this is a Lagrangian fibration. Lagrangian fibration. And so this is what we get this way. Okay, so these are all of the things that we got last time. Okay. And so now, what we can do is, so, and we also discussed that, in fact, this guy in here, we discussed that this moduli space, Mukai's moduli space of H is a stable sheaves on this surface S with some Chern character. On here is just nothing but compactified relative Jacobian of these curves of genus 3 over their own linear system. So for every point of the linear system which gives you a curve, this moduli space gives you a sheaf with pure one-dimensional support on that curve. Sheaf of rank 1. It's not necessarily a bundle because the curve can become singular and the bundle property cannot be preserved, but it becomes a pure sheaf at least. And that's why this is the compactification. That's what the compactification is.
How does a singular structure look?
In here?
Yeah, the whole space, total space.
Oh, the whole space?
Yeah.
It's a smooth.
But total space is smooth.
Yes, total space is a smooth.
How about the Lagrangian fibration, the fiber?
Oh, the fibers? So the base is also so let me see. Let's just see what it is. Well, I think that's a smooth too. I mean, this is a smooth. This is a smooth.
The fiber must be smooth, non-smooth somewhere. I mean, the total space could be smooth, but the fiber
Yeah.
could be not smooth.
The fiber is realized by so for F, the fibers are basically given by moduli space of pure sheaves on a curve,
Right.
basically. And so it could be, it could be non-smooth. I need to think about the cotangent sheaf and see if it is jumping in dimension. Yeah, probably it is non-smooth.
How does it look like? How would I'm interested in knowing the singular structure. Is there any way to understand?
It is not hard to understand the singular structure. At least you can see what kind of a,
Yeah.
what's the dimension of the basically obstructions and so on. But then if you want the way you want to understand it, I don't know. I haven't thought
I
about
mean, the
it.
singularity is to be relevant to physics.
Uh-huh.
So it's to be interesting to
Oh, I see. Okay. Yeah. 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 But anyways,
Okay.
so this is that, and now we can do integration theory. So we have now m of h1 of y1 over s, and we have these two restriction maps r1 and r2. So this compactified Jacobian m of h2 y2 over s. And so we have this simplified picture, and then what we can do, we can basically, via these two maps, we can construct a diagram like this. So m1 times m2 over the diagonal. So first of all, this goes to m1 times m2, which is sending us to the Jacobian. And then there is the diagonal embedding of the Jacobian inside here, and we can take the product of m over the diagonal in here. So we have a diagram like that. And so this is R1 comma R2. This is this map, this is the diagonal embedding, and the fiber product over the diagonal gives us that. And then the statement of degeneration formula is the following. Statement of degeneration formula is that basically the virtual class of the generic fiber of the degeneration is given by summing over all different partitionings of Chern character. So Chern star given Chern star 1 plus Chern star 2 subject to compatibility. So compatibility, so basically Chern star 1 restricted to S and Chern star 2 restricted to S must match of the Gießen pullback of the product of these two cycles via the diagonal map. So M1 virtual times M2. So it is really like inside the middle six-dimensional space, the virtual cycle here, this virtual cycle of M1 in here sits inside A3 of M1. The virtual cycle of M2 sits inside A3 of M2. And so what you can do, you can push them forward via these map R1 and R2. And you're intersecting them with each other. Of course, you need to intersect that as you dualize one, and somehow in the diagonal, on the middle cohomology of this thing, actually you dualize one and intersect it with the other. Which is also matching with all of the intuition we have from differential geometry and Lagrangian intersection theory and things like that. It's just in the level of virtual cycles. These things are kind of, as we discussed last time, derived categorically Lagrangians inside this ambient space. So that is the virtual, the degeneration formula. And the fact that the virtual cycle is preserved along the degeneration tells you that the generic fiber of this degeneration has a virtual class that matches with this Lagrangian intersection of these two things. Except that here we have so many ways of breaking the Chern character into Chern 1 and Chern 2, so we need to add over all possibilities. The same exact formula holds for Gromov-Witten theory. Exact same thing. Where we break the curve classes, beta 1 and beta 2, and here we have the virtual class of stable maps moduli based on one side and the relatively stable maps moduli based on the other side. So then, basically, degeneration formula for dt invariance is integration of this formula. So degeneration formula for dt invariance is given as an integral against these virtual cycles. But let us not forget that this is virtual dimension 0 because original Quintic threefold is a Calabi-Yau threefold. It's virtual dimension 0 moduli space. This is a quartic. So this Y1 was a quartic inside P4. And it's virtual dimension 3. And this is virtual dimension also 3. This is some blow up of P3 along that curve. So if you want to make sense of invariance, over here you need to integrate just constants. Over here you're integrating some three-dimensional class, cohomology class, and over here as well. And so this is basically what we are getting. Are there chalks here? Okay. dt invariance of x5 with Chern character H is stable sheaves on xy with Chern character star, which are given as integrals of 1. These things are going to be equal to Chern star 1 plus Chern star 2 is equal to Chern star plus compatibility dt invariance of H2 stable sheaves on the relative moduli space of Y1 relative to S, Chern star 1. I need to be integrating some class alpha 1 times, literally times, dt invariance of H2 stable sheaves on Y2 S, Chern star 2. I need to be integrating some class alpha 2. This class alpha 1 needs to sits inside degree 3 Chow cohomology of the moduli space M1. This class alpha 2 also same. So this invariant is integral of alpha 1 over 3-dimensional virtual class of M1, and this invariant is integrate of alpha 2 over 3-dimensional virtual class of M2. And, well, how do you know what alphas to integrate, right? Well, there is a detailed analysis. So basically inside this, it kind of that Lagrangian intersection tells you what it is. You have the virtual cycle of M1 and you have the virtual cycle of M2, and you have this ambient 6-dimensional Jacobian in the middle. And you push forward virtual cycles in here and virtual cycles on the other side. You need to look at the middle cohomology of the Jacobian. Then you might generically at least, okay, middle cohomology is the biggest space there, but at least integral third cohomology of Jacobian is controllable. So you need to look at the generators of the middle cohomology and somehow find a way of writing push forward of this virtual cycle with respect to those generators, and push forward the other one also with respect to those generators. When you write that, intersecting is basically intersection of those generators of the middle cohomology. And there are people who have worked on these things like Hassett and this guy in the Minnesota, I forgot the name. Anyway, so people have worked on the cohomology of compact by Jacobian, especially the middle cohomology. So that basically tells us what these alpha 1 and alpha 2 are, and I will tell you what they are. So for us, this tells us that, so let me write it this way at least. It turns out that up to multiplication by some topological constants, alpha i's are given by, and I'm going to draw for you a diagram, Ri upper star of P upper star of the point class. And what does this mean? I will draw for you a diagram, and now you will see what those alpha i's are. So you have M1, relative moduli space. This is R1. You have the Jacobian over the linear system, and you have M2. These are R1 and R2, and there is this map P, and this is the linear system. So this is what alpha is. The very fact that this is a Lagrangian vibration, this tells you that if I pick a point, class in here, in A0, if I pull it back to the relative Jacobian, it will be a three-dimensional cycle. But this ambient thing is six-dimensional, so if I pull it back again, I will get a three-dimensional thing. Okay? So really, alpha i's are, both of them are given by pulling back point class along the Lagrangian vibration, and then pulling back one of them to M1 and one of them to M2. I'm not saying these are the only generators, but I'm just saying the result of integration can be written with respect to only integrating these classes up to some topological constants. That's what I'm saying. Okay, so that's that. Okay, now I can discuss with you modularity. So let me tell you about modularity. In this way, dt generating series of x is given by dt generating series of the two relative guys in the level of generating series. So this guy summing over all n and all betas such that beta times h is equal to I of the dt invariance of h stable sheaves on x phi with the given Schrödinger x there 1, and I keep track of the degree and n. And similarly, this generating series is given by a double sum of such dt invariance of the relative modularities, and this one as well. So if you add everything, then you will get the generating series dt1 and dt2, and you would like to know whether these things are modular. So claim is that each one of these pieces are modular. So this is modular, and this is also modular. And why is that? It really has to do, again, with this vibration structure. So let me tell you, what does it mean to integrate over this moduli space? We are trying to, that generating series in the red here, this is the integral over M1 virtual of pullback R star P over upper star of a point class from P3. So let me tell you why this thing, how is this thing related to modularity? Okay. So let me show you. So this is my picture. I have Quintic threefold. And this is my K3 surface S. It's a K3. And I'm looking at sheaves in here Okay, so let's not do anything. So this is our Quintic threefold, and then I'm also looking at this linear system of genus 3 curves in here. So it's a P3. Maybe this picture shows you what's going on. So I would like to understand what does geometrically this integral mean. So geometrically it means the following. If you are in this P3 and you pick a point, well, this is not every P3. This is the P3, which is the linear system of curves of genus 3 on the K3 surface. So when you pick a point in here, generically, as soon as you do that, that picks out for you some curve of genus 3 in here. So if you want to know what's the fiber of the relative Jacobian over a point in that P3, of course it's the sheaves. All of the sheaves with pure one-dimensional support, which are supported exactly on that curve. So the fiber of Jacobian on a point in P3 are basically sheaves which are supported here. And then you can also ask, what's the fiber? Okay, so let's look at this image of this map R1. And of course, it injects inside here. Then you can ask the question, what's the fiber of image of this restriction map on a point in P3? As soon as you will get sheaves supported on this curve by construction, because this is a curve of intersection, that tells you there must have been sheaves supported on hyperplane section of the actual Quintic threefold, whose restriction to the K3 is those sheaves supported on this curve. So there must have been sheaves supported on hyperplane sections whose restriction to this curve gives you the sheaf that you want. So, but this is a Quintic K3, and these supports are also hyperplane sections, so these are also K3 surfaces. And then there's a linear system of these K3s. So what is this contribution? Basically, this integral, I can now write it down. This integral is the contribution of a unique pencil of K3 surfaces in Y1 in the Quintic threefold to the DT theory, DT invariance of Y1. Contribution means that inside the Quintic threefold, we are not looking at all sheaves supported on hyperplane sections. We are just looking at those sheaves which are supported on the members of a pencil of K3s inside. As soon as you generically pick a point in here, you uniquely get a pencil of hyperplane sections in there. And of course, your sheaf moduli space would just be localized to sheaves supported on the members of that pencil. This is the nice thing about integration. Whenever you see Gromov-Witten theory, in Donaldson-Thomas theory, you're integrating a class, often geometrically. That also gives you a way of localization. You see, if this class is a point class coming from the base curve, it's basically saying that when you look at the fiber of your moduli space over this point, this is that invariant that you will get. So instead of calculating all invariants of the Quintic threefold, you're just calculating the invariance of the fiber of the Quintic threefold moduli space over a point in P3. This is amazing because your calculations now actually you can do it. Also, geometrically you know what it is. You're just counting these sheets. This is very nice. So if you integrate non-constant homology classes over integrals, at least when I see that, I get a bit happier. Because I might think that maybe there's some localization picture like this going on. Of course, that's not always the case, but. Okay, so that's that. And now, why is this modular? So, let C be the base locus of the pencil P of hyperplane sections passing hyperplane sections above, obtained above. And this P is, of course, subset of the linear system of hyperplane sections of Quintic. It's a linear one-dimensional subspace, vector space, subvector space of that linear system. So let C be the base locus of this P. It's this curve. Now consider y tilde 1, which by definition is the blow-up of y1 along the space locus. Whenever you have a variety, you can blow up the variety along any locus you want. And here we are blowing up this Quintic threefold. This is our y1. We are blowing it up along this curve. What happens is that every point on this curve, C, this is the base locus. Every point of this curve will be replaced by a P1 fiber. It's a blow up. And so what happens to the hyperplane sections? They will be stretched out somehow, right? It gives you an accordionic extension, a stretching of this pencil. So you will get that y1 tilde as the surface vibration becomes a surface vibration over P1. In particular, because hyperplane sections of Quintic are Quintic surfaces in P3 and your K3 surfaces, this becomes a K3 vibration. In particular, a K3 vibration. So basically, y1 tilde, if you want to have a local intuitive picture of y1 tilde, it becomes something like, these are members of that pencil, these are those surfaces, things like that. And this is a base P1, and this is a copy of base locus C, and this is also a copy of base locus C, and so on and so forth. And then the sheaves that I drew here in orange, the sheaves which were supported on this pencil, after blow up, they will be supported on the fibers of the K3 vibration. And so this is exactly telling you that the DT invariants of the relative moduli space, which are given by these calculation of sheaf invariance of sheaves supported on these guys, after blow up, becomes the DT theory of a K3 vibration, which is what we have studied in the first two lectures. But this is what I meant where if you use degeneration technique, one good thing about it is that you can reduce the problem to more structured things. So this is exactly that. So our problem DT theory, so DT theory of y1 relative to S with first-chain character gets related to, just related via blow-up construction to dt invariance of K3 fibration on T1. So this is from lectures 1 and 2. And guess what? I mean, we calculated these things, and the dt generating series of y1 tilde with the Chern character y1, Chern 1, was a modular form. It was actually given by some theta function of Borchardt, which was keeping track of the Noether-Lefschetz numbers, divided by some Dedekind or discriminant Kospodov form of weight 12. It was a vector valued modular form because this guy was vector valued and this guy was a scalar valued. So each component of this vector valued guy divided by this guy would be giving you, in each component you would have a scalar valued modular form of weight minus 3/2. So as you can see, we have degenerated Quintic threefold into a quartic and almost a P3 or a blow up of P3. On the quartic side, the relative moduli space, integration against the virtual class of relative moduli space becomes integration of some cohomology class coming from some P3. It somehow becomes a local integration. And then the integration of the relative moduli space Y1 becomes counting sheaves supported on a pencil of hyperplane sections passing through that K3. And then after blow up, this becomes a K3 vibration itself. But then the real question is, what does it mean? If you blow up Y1 against the base locus of some linear system inside Y1, which is here, it's not the same geometry. The geometry has changed. So the question is, how can you possibly relate this dt theory to this dt theory after blow up? So that also has to do with some very nice geometric construction, which we also learned from work of Yau and company, as well as Ponte used it, and many people used it. So let us see how to relate the relative theory to dt of the blow up. I can just show you in a picture. So let's do the following. Consider degeneration to the normal cone of y1. This is the quartic in P4. To the normal cone of y1, to the normal cone of S inside y1 of y1. Degeneration to the normal cone is, of course, a famous object. So what does that mean? You have, so let me draw, if I draw for you 3D pictures, I think it's better. So this is your y1, quartic in P4. This is that S, K3 surface. You degenerate this thing into the normal cone of this K3 surface. So you will get some, again, normal crossing. And what is it? One piece of it sees just y1. The other piece of it is the normal cone of S inside y1. What is the normal bundle of S inside y1? This is a hyperplane section, so it is just O of 1. So what this is the projectization of O of S plus OS of 1. normal cone of S in Y1. Now let's keep track of, so note that y tilde 1 was defined as blow up of y1 against that base locus of P, that pencil P. That was a curve of intersection. That base locus, let's say, is in here. So you have some family over A1, and for generic members of the family for t not equal to 0, you have a curve which is the base locus of that pencil of hyperplane sections of y1 that pass through a given hyperplane section, S. So for the generic members, this thing actually, you can always see it, the curve. And then what happens over the degeneration? Naturally, via this degeneration, this guy has a limit. And this guy sits inside the zero section of this cone. So if this is the cone, if you really want me to tell you what's going on, this cone is like a cylinder. This is the infinity divisor of this guy. So this is something with P1 fibers. This is a P1 fibration on the base surface S, because this is fibers of this one is P1. So this is the infinity section, and this is the zero section. And S naturally sits as the zero section inside the cylinder. It sits in here. So this is the actual S, and this piece is isomorphic copy of S. So this piece is also isomorphic to S, but it's the one that sits inside the infinity section. But then, the curve that you're looking for has a limit that sits naturally in S. So it sits naturally in the proper transform of S given by the zero section inside the cylinder. So this curve C has a limit that sits inside here. So limit as t goes to 0 of C of t is equal to C0. Okay? Now, let's define some locus inside the total space of this degeneration. Let C bar be the kind of union over all t of in A1 of C of t, closure of that union. So this is a closed subscheme over A1. It's a closed two-dimensional subscheme inside this fourfold. This is a fourfold. The total space of this is a fourfold. And inside there's a closed subscheme I can define by taking the closure over all values t of C of t. And taking the union. Okay? So then what I can do is let I don't know, this kind of y be the total space of y1 degenerated into y1 union over S with normal cone of S. This is the total space. And now I can blow up this fourfold in the total space along this guy, this locus. So consider y1 tilde given by blow up of y1 along this locus. Then you might ask, what happens to this picture? This is what is, if you like, you can call this simultaneous blow-up. What it does is that, when you look at this picture, every generic member of this threefold degeneration will be blown up along the fiber of this C bar at that T. So if you ask me what this is again a family over A1, where over the generic member of the family when T is not equal to 0, what this guy does, it blows up Y1 along C of T. So here you will see blow up of Y1. Okay, so the notation is a little bit bad, so let me call these things like that. Something like that. So what happens is that every generic member of this family will be blow up of Y1 along C of T, for T not equal to 0. But this is exactly Y1 tilde, by definition. And then, what happens over the special fiber? The simultaneous blow up, what it does, it takes the special fiber and blows it up exactly along fiber of C bar at T equal to 0. But fiber of C bar is the C0 which sits in the 0 section of this cylinder. So what happens? This normal cone will be blown up along this curve. So it will be Y1 union with S, blow up of the normal cone at C0. But what is the point I'm trying to say is that this is a really delicate but beautiful geometric aspect of this. C0 sits inside the 0 section, not the infinity section. So when you blow up this variety along this curve, this part of the variety, Y1, does not see the curve. So in fact, that's why I'm writing after blow up, Y1 is just gets proper transformed up to the blow up. So Y1 stays as it is, but this piece will be blown up. This is extremely important because we want to keep Y1 as it is. And now if we use degeneration technique, then we can see that the dt invariance of the Y1 tilde will become the sum of the product of dt invariance of Y1 relative to S times dt invariance of the blow-up cone relative to S. So there you go. If you have some variety, the relative theory of that variety now is related literally to the invariance of the blow-up of that variety. If you did this thing correctly, if the curve sits inside here, you don't see this phenomenon. Then because this thing will be blown up and you will lose data of Y1. But we are in luck because this is geometry and this doesn't happen. So this way you can see now these two things are related. So this thing is the one that we talked about. This is the K3 vibration, which is modular. And you would like to see if this thing is modular. So if I can prove to you that this guy is modular, we are done. So modularity of this thing has to do with proving modularity of this guy. And the fact that, we are talking symbolically here. These are some of the double sums. This is a very, very ugly thing in here. But somehow we are talking symbolically in the sense that somehow we are trying to say there's a huge ugly sum in here and a huge sum in here. This sum is a modular 4. And if I can prove to you that every coefficient of this particular part of the sum can be computed with respect to data here and data in here, it's like I'm inverting this piece and putting it in here, then it's a modular 4. If this one is modular 4. So maybe the question is this thing modular 4 or not? Of course, then you can see in these kind of business, you can see that this notion of invertibility, for example, Pontripanti and Pixton, when they wanted to prove the MNOP conjecture, correspondence between Gromov-Witten theory and Donaldson-Thomas theory, they had some statements like this. They had a huge sum on the right-hand side, and they needed to prove some statement like this. They called it invertibility. It means that coefficients in here, can they be computed with respect to these things and these things? In some sense, inverting this thing. Okay, so now I have this picture which I would like not to delete. Why is it that this blow up has a modularity property? So let me read off now the way we try to write it in our paper. So there's a theorem we can prove. Okay, so let me then prove the following. This was the geometric construction. If you think that this is kind of maybe too much detail and a little bit confusing, of course that's why we are recording it. And if you want to look at it later, you will see it. And it's a nice, very beautiful geometric picture. Okay, so then now we would like to understand the moduli space of sheaves. So maybe I should have said MH, let's say MH1 and H prime 2. So a statement is the following proposition. A generic point Q in the moduli space of H2 prime stable sheaves on blow up of this normal cone. So this is the normal cone of S inside Y1. It's blow up along this curve C of sheaves with, or supported on here with some Chern character star prime 2 is given by a sheaf F as I lower star of G, where G is a sheaf with Chern character of G equal to 1, H prime 2, and some number n, supported on a hyperplane section H2 prime inside this guy. Normal cone of S inside Y. Okay, if I draw for you a picture, it will become very, very easy. What is the generic point of the moduli space of sheaves in here? Here, it's a quartic and we have a pencil of hyperplane sections in here. This guy doesn't have that property. In fact, the sheaf that we get over here is supported on some surface like that. This part of the boundary of the surface meets that curve of this part meets that curve of intersection C0 with respect to which we blew up, and this part of it meets the K3 surface as at an isomorphic copy of C0. This red surface is what I'm calling H prime 2. A generic member or point in the moduli space of sheaves on this blow-up is a sheaf supported on A1 hyperplane section in here. That's it. It's a sheaf which is pushed forward of some torsion-free sheaf. So I here is the map from H prime 2 onto this threefold blow up of the normal cone of S inside Y1. That's it. Okay? And so, as soon as you realize this, then the modularity property of this degenerating series becomes immediate. If you have a sheaf which is torsion free and rank 1 over here, then then we can show hence it's easily seen, hence it's easily seen that this generic member F is isomorphic to ideal sheaf of some curve, so ideal sheaf of bunch of points tensor with some line bundle on this member H2. Basically what I'm trying to say is that on the second part of this degeneration, your moduli space becomes moduli space of a sheaves of rank 1 on the surface, and then those are torsion-free sheaves of rank 1, but by what we discussed in the previous lectures, which are twistings of ideal sheaf of points. So via this twisting, you can actually see that your moduli space effectively becomes Hilbertism of points on this surface. So then MH2 MH2 prime is the same as Hilbert scheme of points on H prime 2. But remember that all of these things are relative moduli spaces. So if you have Hilbertism of points on the surface, it means that these points cannot meet. These points need to meet and intersect with the relative divisor in the middle transversely. And then from topology and from manifold theory, we know transverse intersection of a point with any subvariety is empty intersection. So this is what we call relative Hilbertism. Hilbertism of points which have empty intersection with S, hence the relative Hilbertism. Empty intersection with one thing. So let's call this thing C infinity. They have empty intersection with C infinity inside S. So it's C infinity. Hence the relative Hilbertism of n points on this H prime 2 relative to C infinity. That's it. So your moduli space of sheaves on the cortex threefold degenerates into relative moduli space, which we wanted to capture its modularity. So moduli space over here after blow up becomes the moduli space of sheaves on K3 vibration. It has modularity property. And then this is the relative moduli space. This is the question mark. We didn't know what it is. And then this piece. And the DT invariants in here are invariants of relative Hilbertism of points on one surface relative to a curve. So you look at points on this pink surface, which are not supposed to lie down on this divisor C infinity. We call that relative Hilbertism. That's it. And so that will almost finish my talk because we have proved the theorem that we wrote a paper, we published it in, I think, Asian Journal of Mathematics. And then this was the so the GT invariant of H prime 2 stable sheaves on this blow up of the normal cone of S inside Y1 to some Chern vector star prime 2 is given by the integral over the Hilbert scheme of points, relatively small points with respect to this divisor C infinity of the Euler class of some sheaf L, nu, where nu is the locally free sheaf on the Hilbert scheme, on the relative Hilbert scheme, whose fibers at every point some ideal sheaf of some length and subscheme is given by x1 I of z twisted by minus this divisor. And so we calculated this generating series and we got a modular form. So we calculated the dt generating series on this blow-up normal form of S inside Y, and it became something like some eta function of Q, this time to some different power. So it was basically it was to the minus integral over S of tangent bundle of S twisted by minus C, something like that. And this is the product 1 minus Q to the n. Okay, so it becomes a modular form. So the final comment is the following. So when you prove this thing, dt invariance of y1 tilde, which is the K3 fibration, becomes dt invariant of y1, the Quintic with respect to the surface, times this dt invariant, blow up of normal cone of S inside 1, relative to S. The statement is that by previous lectures, this is modular. This one is by what I put over there is modular. So this gives us modularity of this thing. And then by the first degeneration technique, this dt of x5 is dt of y1 over S times dt of y2 over S. So now we have proved only one piece, which is y1 over S. We have proved that this is modular. And then for y2 over S, we also get some phenomenon like this. We get the Hilbert scheme in here, and we can also prove modularity of this one. So after that, we get the modularity of this one. Okay, so this is the procedure to prove the conjecture of S-duality on Quintic threefold. Now, so my voice was disconnected with that. So the proof is not complete, and the reason is because, as I told you, first of all, the construction of this degeneration technique for general sheaves is not there. That's one reason. Second of all, when I was writing this integral as a local integration of some cohomology class, this one as a cohomology class, I talked about those topological constants. What I'm not sure is that do I get a constant or do I get a series of constants? If I get a series of constants, probably that itself could be a modular form. As I change the Chern characters and so on, because the Chern character in here is now split into Chern 1, Chern 2, and you need to add over all possibilities. And that has somehow to do with some analysis over the compactified relative Jacobian. This is why this problem is still open. And when I looked at the generating series we obtained, it was not the same as the one predicted by the string theorists. And I think probably it's because of those topological constants. So that's why it's exciting, because we have not yet proved anything. But we know a lot about it. We almost know how the proof is. Almost. But really, it's a hard problem. If you can figure out those issues, then you have proved, in my opinion, one of the most important conjectures in the string theory. Why is it important? Because, as I mentioned earlier, this weight, modular weight minus 3/2, that keeps happening in the string theory, this is pretty geometrically interesting, because it seems like no matter what your threefold is, if it is a K3 vibration, you get the same weight. If it's a quintic, you get the same weight. I mean, this is very, very bizarre. And we have gotten this weight minus 3/2 for other types of geometries too. So I don't know what is special about minus 3/2 actually. It feels like itself an invariant somehow. So yeah, nice stuff.
Is this the last section you gave?
Yes, so this is the last section on DT theory, but then